Okay, Giancoli 5152. Um, so we'll talk about kinematics of circular motion. So here's uniform circular motion. It's when the motion of an object is in a circle, right? And the radius is constant and the speed is constant. So the speed here is the speed here. Velocity always goes tangent to the circle. So if this thing's going in a circle, the velocity is always going to be a tangent line off of the circle. So looking at the change in velocity, and we're going to do a little bit of calc here, is that in a limit, the time interval becomes really, really small. So here's what we see, right? This is what happens, and you can see that, and you can see we can continue to get closer together, but the time limit gets smaller and smaller and smaller. We can take a look at this, of the difference in the vectors, and here's what we get. So there's the math, but here's the reason, or here's the equation that goes along with it. Acceleration, okay, equals v squared over r. So velocity, the constant velocity squared over the constant radius. So that's centripetal acceleration. And why it's called centripetal acceleration is that it points toward the center of the circle. So velocity goes this way, all right? Centripetal acceleration always goes in. So when an object's going in a circle, in uniform circular motion, acceleration always points to the center of the circle, always. And again, we'll see that when we do sample problems. So acceleration of a revolving ball. 150-gram ball at the end of a string is revolving uniformly in a horizontal circle of radius 0.6 meters. As you can see in this diagram, right? The ball makes 2 revolutions in a second. What is its centripetal acceleration? Do it now.
All right, so you read the problem to you. The problem says, there it is. A 150-gram ball at the end of a string is revolving uniformly in a horizontal circle of radius 0.6 meters. And there's a diagram there. The ball makes 2 revolutions in a second. What is the centripetal acceleration? Okay, so a couple of things. One, mass always has to be in kilograms. So I got to convert this to kilograms. We just move the decimal 3 to the left, so it's 0.150 kilograms. So that's my mass. My radius is in meters, so that's good. And now we want to get our velocity in meters per second. So if we do 2 revolutions per second, there's 2 equations I want to show you other that I haven't shown. This one's centripetal acceleration is v squared over r. Got my radius. Once I find v squared, I'll be good, and I'll be able to solve for the centripetal acceleration. So this first one, t. T's time period, how long so it's just a length of time, right? Frequency is this f. Frequency means per second. So let's say I do 2 revolutions per second, right? If I put 2 in for frequency, so 2 equals 1 over 2, right? My t is 1/2, or my t is 0.5. So essentially the t is how long it takes to do 1 revolution. So if it takes 2 per second, it would do 1 revolution in half a second, all right? So now I know my time period's half a second. So my time period's half a second. Now, velocity is distance over time. My distance around the circle is the circumference, 2 pi r. So if I take 2 pi, multiply it by 0.6, divided by the time of 1 revolution, which is 0.5, that should equal my velocity. So let's test this out and see. We got 2 pi. Whoa, 2 pi, here we go, times 0.6 divided by 0.5. I get 7 point, and I'm going to go 3, that's 3 sig figs. I'll stay 3 sig figs. 7.54 meters per second. So that's going to be my velocity in meters per second. So what we did is we took revolutions per second, took the inverse, which told us the time to do 1 revolution, and then we found the circumference of a circle, which is the distance of 1 revolution. So the distance of 1 revolution divided by the time of 1 revolution gives us the velocity, 7.54 meters per second. And now, to solve for centripetal acceleration, I take 7.54 and square it, divided by my radius, 0.6, and that would be my centripetal acceleration, 7.54 0.54 squared divided by 0.6 equals 90, yeah, 3 sig fixed, so 94.8 meters per second squared. So don't forget those two equations. They'll be on the board, but they definitely will be beneficial.
Moon centripetal acceleration. The moon's nearly circular orbit around the Earth has a radius of about 3,000 or 384,000 kilometers in a time period of 27.3 days. Determine the acceleration of the moon toward the Earth. Do it now.
Okay, so we're looking at the moon and the Earth here, and we see that the moon's nearly circular orbit around the Earth has a radius of about 384,000 kilometers and a period t of 27.3 days. We want to find the acceleration of the moon toward the Earth. Okay, so we want to find the acceleration of the moon toward the Earth when that's the radius and that's the time frame. So first thing we want to do is we want to look at our distance, right? And our distance of our radius has to be converted to meters. Just move the decimal 3 to the right. All right. So now our distance, remember our distance is the distance around, so that's going to be our circumference, which is 2 pi r. So if I take my radius in meters times 2 pi, that will be what goes here. So I'm just going to put 2 pi times my radius of 384 million meters divided by my time. Now my time has to be in seconds, so I'm in days, and we just do some conversions. 1 day, 24 hours, 1 hour has 3,600 seconds. And so I've bounced through that, and my calculation is 27.3 times 24 times 3,600 equals, and I'm going to round this to 2 million, all right, 2,360,000 seconds. That's a lot of seconds, all right? So I got my time in seconds. So I put this here, and now I'm going to have meters per second for my velocity when I solve this. So that's what I want, right? So now I take 2 pi times 384 million divided by 2360, 1, 2, 3 zeros, and I get 1,020 meters per second. Again, I kept it at 3 sig figs. It's a little bit more than that, but that will suffice. So I have my velocity. So that's the velocity that the moon's traveling this way, right? But I want to find the centripetal acceleration. So acceleration is v squared over r, my velocity, 1,020 squared over my radius, but I want my radius in meters, so I want to use this number, not that number, 384. Boom. So 1020 squared divided by 384, 123, 123. And I get 0.003 meters per second squared. And that is how much the acceleration due to gravity is, right, from the moon to the Earth. So you can kind of see the moon pulling into the Earth pulling into the moon, not much acceleration there going inward. Okay, but that's your answer. Don't forget, meters and seconds are what we want when we solve for the velocity, and don't forget your 2 pi. I almost did.
So using now dynamics, the uniform circular motion, so we're going to take Newton's second law, F equals ma, and apply it. So if an object's in uniform circular motion, so we have this object in a string and we're spinning it, right? The velocity is still going to be tangential, so it's going to still be a tangent going off. But since acceleration goes in, the force also goes in. We call this the centripetal force. So force is equal to ma. If we take our previous equation for acceleration, v squared over r in for a, we get m is equal to, or F is equal to mv squared over r. And so this is the centripetal force that we're talking about here, the center-seeking force, which in this case is just going to be tension. So the force must be inward by thinking about a ball and a string. So anytime we have a circular object going in a circle, there is a centripetal force. Again, there's a string. Now, if this was a planet orbiting another, or a planet orbiting the sun, this force would then be gravity. So this force can vary. It has to be one of our forces, but it's always centripetal because it's center seeking, and that's in uniform circular motion. Now, there's another word that comes up, centrifugal, and there's no such thing as a centrifugal force pointing outward. All right, so what we mean by that is if an object's in a circle and the string breaks, there's no force causing it to keep going out that way. All right, once that force disappears, there's no force acting on it. So what happens is that the object will move in a straight line. It flies off tangent to the circle. So it breaks and it flies off at a straight line. So when it breaks here, it doesn't go this way, it goes this way. And it's because once that force is gone, there's no net force acting on it. So it's going to continue on a straight line, acting like it always has before at a constant velocity. That's Newton's first law, right? So once that force is gone, once the unbalanced force or the centripetal force is gone, its inertia kicks in and it travels this way. Okay? So when centripetal force disappears, it goes with a tangent because of its inertia. So here's an example of a force problem. Estimate the force a person must exert in a string attached to a 0.150 kilogram ball to make the ball revolve in a horizontal circle, a radius of 0.6 meters. The ball makes 2 revolutions per second for a time period of half a second. Ignore the string's mass. Solve it now.
All right, so now we're going to use some dynamics here. We're going to look at Newton's second law, F equals ma, and we're going to apply it. So we have our object on a string, right? We're flipping it around horizontally, so we're doing a circle this way, and so it's going like this, right? A horizontal circle. And we know the radius of our string is 0.6 meters. We know the mass in kilograms of our ball is 0.150, and we know 2 revolutions per second, which we've already figured to be a t of half a second. So when we look at F equals ma, if something going in a circle, my acceleration in a circle is v squared over r, so F is essentially mv squared over r. So this is Newton's second law as it pertains to objects moving in a circle. So when we look at this, right, we have velocity going out this way, we have acceleration going in, and that force is going in, that force of tension. So that's what we're talking about. We're talking about the force of tension on this string, okay? And we're ignoring the string's mass, which we could add if we needed to, but we're not going to worry about that. Okay, so let's see what we can do here. We're solving for force, mv squared over r. We know m. We know r. We got to find v. V's distance over time, and we did this math already, but we'll do it again. Distance in a circle is 2 pi times my radius over my time period. And we will put that in our calculator one more time. 2 pi times 0.6 divided by 0.5, 7.54 meters per second. So that's our velocity. Now I just go to this equation and I substitute. The mass of my ball is 0.150. It has to be in kilograms. My velocity is squared in meters, and then I'm also doing 0.6. And we'll talk about units here before we finish. But when we solve this, 0.150 times 7.54 squared divided by 0.6, 14.2. So 14.2 newtons of force. Now let's look at units really fast, just so we can show you this. All right. So this is in kilograms, and I'm multiplying it by meters squared per second squared, and I'm dividing by meters. So when I get my units, right, this cancels out one of my meters. I get kilograms times meters per second squared, which is a newton. So that's why the units come out newtons still, even though it's the acceleration units are still meters per second squared. That's just how it all fits together unit-wise. And that's why our answer is what it is.
Okay, so here's a vertical circle. A 0.150 kilogram ball on the end of a 1.1 meter long cord is swung in a vertical circle. Determine the minimum speed the ball must have at the top of its arc so that the ball continues moving in a circle. And then calculate the tension in the cord at the bottom of the arc, assuming the ball is moving at twice the speed from what you get in part A. So here's the picture, and we'll talk about that. Do it now.
All right, so we're spinning a ball, vertical circle, so it's going like this, right? Instead of like this horizontal, be vertical with the string. Okay, so we're flipping the string like this, and we want to find the forces acting on this ball. So up here at the very top, we have two forces. You got gravity, and then you have tension, both going in the same direction. At the bottom, you got tension and gravity. And we want to find, this question's asking us to find the minimum, I think, the minimum speed the ball must have at the top so that the ball continues moving in a circle. So minimum speed at the top. So Newton's second law. I have two forces. I have tension and gravity both going down. So, I mean, I'm going to keep them both negative, I guess. Negative minus equals, right? V squared over R times my mass, which is M. Now, if I'm keeping at minimum speed, that's the minimum speed required to keep that thing going. My tension is going to keep getting smaller and smaller until it's 0. So when I talk about minimum, I'm saying no tension. So my tension's 0. So now Fg equals V squared over R times M. The force of gravity, as we all know, is just mg is equal to V squared over R and times M. M on both sides. I can divide both sides by M. Or you can put the mass in if you want. But G, in this case, is going to be V squared over R. So think about everything we know. We can assume we're on Earth, so G is going to be 9.8. V squared is my minimum speed, and then this is 1.1 is my radius. So if I take 9.8 times 1.1, and then take the square root of that answer, I get 3.28. So that means the minimum velocity to keep this thing turning would be 3.28 meters per second. Anything less, and the ball would just fall. It wouldn't have enough to keep going, okay? So that's at the top. So now we want to find the tension at the bottom, assuming the ball is moving twice the speed of part A. So at the bottom, here's what we got. We got tension going up, force of gravity going down. So they're going in opposite directions. So I'm going to say force of tension minus force of gravity equals ma. And that's just the second law. Force of tension, we're trying to find if the velocity is twice as much as this, okay? So my force of tension's here. My Fg is going to be 0.150 times 9.8 equals mv squared over r, okay? I'm going to keep substituting here. Ft minus 0.15 times 9.8 gives me 1.47 equals 0.150 times 3.28 times 2, 6.56 squared over my radius of 1.10 meters. So Ft minus 1.47 equals 0.150 times 6.56 squared divided by 1.10 equals 5.87. Add this to each side. 5.87 plus 1.47 gives me a force of tension of 7.34 newtons. And that's what would be required to get the ball moving twice the speed as up here. So I would have to go from adding 0 tension force to 7.34 newtons of tension force on the string to allow this to happen.
Okay, last thing, conceptual example, tetherball. So we got tetherball, and if you've seen Napoleon Dynamite, you know what this is. It's played with the ball tied to a pole with a cord. After the ball is struck, it revolves around the pole like this. So now you can see the vectors and what direction is the acceleration of the ball and what force causes the acceleration, assuming constant speed. So as this ball's going around, gravity's pulling down, you got the force of tension. Now the force of tension is at an angle. Part of the tension force is keeping the ball up. So this part of the tension force is probably going to be equivalent to the mass, or to the weight, right, that's going around. And then there's another force that's keeping the ball in, right? And that's the centripetal force. So the question is, what force causes the acceleration? Well, it's going to be this force. It's going to be the horizontal component only, because that's the only component that's going into the center of the circle. So which direction is the acceleration? It's going to go also to the center of the circle. So the acceleration is also here. All right? And so that's what we see. So it's because this breaks, because this is at an angle, doesn't change the acceleration. Acceleration always goes into the center of the circle, not to the top of the pole, to the center of the circle.